about solar interior and the nuclear energy production at the core of the sun, which essentially powers the total solar luminosity. And we also talked about the solar neutrinos and looking at those neutrinos, detecting them, that gave confirmation to the standard solar models. So today we will go further out. We will talk about the surface and the atmosphere, and about the atmosphere of the sun. What are the structures we see, and do we understand how do all these structures form? If we do not understand, what are the real problems, and so on and so forth. So starting again with the references. So again, most of it you will find in the lecture notes by Sami Solanki, again at IMPRS website. And then the two textbooks I mentioned yesterday also is the Physics of the Sun, a first course, and the Solar Astrophysics by Peter Foucault from Wiley and Sons. Okay, so let us look at this again, the structure of the sun. So in the right we have the structure as an artist understands based on all the physics we understand about the sun and its interior. So you have the interior where the nuclear burning, and then you have the energy being radiated out, and then the convection taking over, and that's the whole region is essentially called the solar interior, and that's where you produce neutrinos, that's where you produce almost all the energy in the solar interior. The solar surface is essentially the surface or the location where the photons which are generated deep down in the solar interior as a gamma ray photon, they are going through so much of collision, they become almost white light photons when they reach onto the surface, and the location from where these photons they start to escape, that location is defined as the surface. Now the surface, or the definition of the surface, depends on what wavelength you are looking at. So for standard purpose, the surface is defined in the visible continuum. So if you take an image of the sun from ground, what you are seeing is essentially very close to what is defined as the surface of the sun. And above the surface stays the solar atmosphere. So the atmosphere is then defined as the layers through which these photons are traveling through, and they are unhindered because the layers above, they are very less, they have very less density, and so they travel. Although there are some photons which are produced because there are various emissions taking place on the way, which we will talk later on. Also some of the photons are being absorbed, so essentially they are getting destroyed, and some photons they also do get scattered, and I will show earlier that whatever you see during the solar eclipses in the outer atmosphere is essentially the photospheric photons, or the photons coming from the photosphere. They are white light photons, they are scattered because of the presence of the free electrons in very high temperature corona. So when we image the surface of the sun, what we see is essentially solar granulation, right, in the quiet area. If you take one area where we do not have much structures on the surface in white light, and we image with fairly high resolution, what we see is solar granulation. So granulation are nothing but they are essentially bringing, they are the convective cells, they are bringing the heat from below and cooling down and then going inside. So for example, in these images, or the sequence of these images, these bright blobs, they are the convection cells, they are coming out as a hot material bringing the energy, and then you have these dark lanes where this plasma then is going in. So creating a cyclic pattern that the hot plasma is coming up and the cooler plasma is essentially going down. Now if you do Doppler imaging, for example, in the same wavelength or the same layer, what you see in this panel here, that you have this intensity where you have bright means hot and the dark means cool, and if you do a Doppler imaging in this, what you see that wherever this is bright in this image here, that is the location which shows blue shift, and the blue shift means that the plasma is essentially coming up, and what you see red, they are outlining this dark region in this intensity animation. So, that proves that essentially the plasma which is coming as a blob, cooling down and sinking in. This observation is taken from a sunrise balloon observatory which went into the atmosphere, observed the sun for like few days and then was stopped. Right. So, let us look into the solar atmosphere. As I defined earlier, the solar atmosphere is the layers through which most photons can travel unhindered, and depending on the wavelength you are looking at, these are optically thin and optically thick. What you see as a surface when you image the sun are as the lowest atmosphere, that is the photosphere. Now, when you observe or take a picture of the photosphere, what you see, the center of the disk is pretty bright over here. Around the disk, you see this dark areas which are uniformly darker all around the sun. In addition, what you see, there are these dark spots which are called the sun spots, and you also have areas which are a little brighter than what you have in the background. They are called the faculae. Right. Now, what does this tell you? Is the sun really, I mean, this is a 2D representation of a 3D object. So, if this is a uniform sphere, then why are we seeing this dark uniform region around the limb or the outer boundary of the disk? And that phenomena is called limb darkening. Now, the other atmosphere you see from ground, and that you can readily see, is during total solar eclipses. So, when the moon comes and blocks the disk of the sun, as I mentioned yesterday, the disk is about a million times brighter than the corona and then the outer region. So, you really need to switch off or rather block the light coming from the surface to see the structure outside, and that is when you see the whole glory of the sun, and the crown of the sun is called solar corona, and that is what is defined as the outer layer of the atmosphere. Now, during these eclipses, what was also found was there are these red patches appearing, if you can see in this image itself, very close to the location where the moon is blocking, and that is defined as solar chromosphere. And what was obtained is, like, if you do a spectroscopy during an eclipse very near to the limb, what you find is the appearance of red ring during the total solar eclipse for few seconds, and that happens at the start of the second contact. So, the moon is coming, here you have the sun, the moon is coming, that is the first contact, and then you have the second contact. So, then you will see the full glorious ring around, and then at the totality end of the third contact, then also you see this red ring appearance around the disk. And since it appears red, and in Greek red means, chrome means red, is called the chromosphere of the sun. And when the spectra was taken, this is an spectra taken during eclipse, what you see, there are appearance of various lines. You have like H beta, helium 1 and H alpha line. H alpha actually corresponds to the transition corresponds to the color which emits the red in your WebGure. What other thing was found was helium was first discovered, which is the second most abundant element in the solar or in the universe. That was first discovered in the spectra taken during one of the solar eclipses, and that was in 1868 in Guntur. That eclipse took place in India. With the success of this spectroscopic technique during solar atmosphere. Again, two gentlemen, Harkness and C.A. Young, they independently took a spectra of during the eclipse of 1869. So, that is the year after when the helium was discovered, and they discovered another line which was forming as a green line at the green wavelength, and that was iron 10. Later on, it was found that you could find many other lines during the spectroscopy, if you do any spectroscopy during the total solar eclipse. And the existence of these lines were very difficult to interpret, because there was no element in the periodic table which could be associated to such elements. And since they had a success story of discovering helium, because helium was also first time discovered in the solar atmosphere, this element was named as coronium because it was supposed to be coming from solar corona. But later on in 1930s, Grotrin and Edlin, they found that these elements are not coronium. These lines are not due to any new element, but these lines are essentially due to very highly ionized heavy elements like iron and calcium. So, how ionized? So, the iron has to be 9 times and 13 times ionized to produce iron 10 and iron 14 lines, and calcium has to be 14 times ionized to produce calcium 15 line. Now, how would you produce such lines in the spectrum of the solar atmosphere? The only way to produce the spectrum in the solar atmosphere is if you have a gas which is more than 1,000,000 degrees Kelvin hot. So, that fixed the problem, or rather that fixed the problem of existence of the corona, where you have the very hot gas, but then it gave other problem, that how could the atmosphere of the sun be so hot, producing these spectral lines being at more than 1,000,000 degrees, because we mentioned yesterday that the temperature of the surface is only about 6,000 degrees. So, we will get back to it in the due course. Here is the composite. So, you have the photosphere where you observe these structures, you have the sunspots, and then on top you have then observe the chromosphere, this ring which is going around the disk, and that is essentially representing your chromosphere. This is not on a scale, and outside that chromosphere you have the corona, which is seen in its full glory when you take an image during total solar eclipse. And outside this corona you have heliosphere, and that goes all the way till the heliopause, where essentially the sphere of influence of sun ceases. What we discovered, that the photosphere is 6,000 degrees, because we can take the black body spectrum, or take the solar spectrum, we can fit with the black body, which is corresponding to about 5,800 degrees. And we then discovered using spectroscopy that to produce these spectral lines which are highly ionized, you need to have a temperature which is more than 1,000,000 degree. That is your solar corona emitting at 1,000,000 degree. In between you have the solar chromosphere, which is again, as I will show, it belongs to various different spectral lines, and that is roughly around 20,000, 30,000 Kelvin. So, what it says, that essentially when you go away from the sun's surface, your temperature slowly starts to increase. It goes from around 6,000 to 20,000 and then jumps suddenly to about 1,000,000 degrees. If you compare what you used to draw the sun would look like during your kindergarten, then this is what you used to draw. Right. Now, if you take the total solar radiation spectrum, go outside the Earth's atmosphere, because all the high energy radiations are stopped by our Earth's atmosphere, for example, EUV and UV. If you go up there and take the solar radiation spectrum, whatever you have above are in the wavelength below 310 nanometers, they are absorbed above the atmosphere. Beyond 310, it all comes to ground. And what you find that you have, of course, the bulk of the radiation is coming in visible, but you have radiation coming all the way in ultraviolet, near ultraviolet, and so on and so forth. And what we now know, that's the region for EUV and UV is essentially your chromosphere and corona, whereas the visible is coming mostly from the solar photosphere. If you do an empirical modeling, one dimensional, to look at the overall property of the sun or the gas which is forming the sun, then what you have is again plotting height on x axis, temperature on the y axis in the left side, and mass density on y axis in the right side. Okay. And what you see is essentially your temperature starts to increase here. It goes and forms a plateau in the chromosphere, then essentially it goes higher up, shoots to 1,000,000 degree in the transition region, and that is what provides an interface between chromosphere and the higher atmosphere in the corona, and then it goes and it stays about 2,000,000 to 3,000,000 degrees. In that region, photosphere and chromosphere produces visible and UV photons, whereas X-ray and EUV photons are essentially coming and producing the transition region and the corona. Look into the height. What you have is the photosphere is roughly around 400 to 500 kilometers, and then from above the photosphere about 2,000 kilometers is what we call as a chromosphere, and beyond that about 100 kilometers, that thin region where the temperature and density, they both are steeply changing. So, temperature is steeply increasing, the density is steeply decreasing, and then that goes into transition region, and above that is the corona. Now, if within the transition region, whatever hydrogen and helium you are observing in the chromosphere and in the photosphere, since the temperature goes to 1,000,000 degree, the whole plasma, the complete plasma you see in transition region and the corona is fully ionized. So, only no hydrogen, no neutral element. So, all you see then high ionization of heavier elements like oxygen, carbon, silicon, magnesium, iron, calcium, etc. Okay, so now what you do is you can make a telescope and tune your filters in that telescope to pick out photons at some certain frequencies, and they have been done it's using multiple instruments. But you also have to remember that if you want to collect the photons which are at EUV and UV, you have to go outside the atmosphere, and that is why space era revolutionized the whole solar physics, starting from IUCAA and SOHO, but before that there were other instruments like Skylab and other rocket flights. So, here is an observation, a sequence of observation taken from Solar Dynamics Observatory. So, put that together, all of these images are taken the same day, almost at the same time. So, there is an H alpha which is taken from ground, that is this image here, and then you have another one in X-ray which is taken from XRT telescope on Hino day. What you find that depending on the frequency band or depending on the wavelength, which is essentially representing different temperature of the plasma, the sun looks very, very different. So, for example, this is your good old photosphere at the left here in this image, and then when you go higher up, then you have the chromosphere, and then you are forming the transition region, and then going all the way into the corona. The structures seem to be very nicely correlated also. This image essentially showing that measurement of the magnetic field that we will talk about in the last lecture, that will happen tomorrow. But what you can right away see that there are structures in the magnetic field map. So, here the white is the positive polarity and the black is the negative polarity, and you can combine that everywhere in all these images, that wherever you have this magnetic field is stronger, the images are showing stronger emission all the way from chromosphere up to the corona. So, what we can infer from this is that the atmosphere, they are not standalone, but they are really strongly coupled with each other. So, you have to treat the sun in a very coupled manner and not only looking at one particular frequency and trying to understand what the sun is all about. Okay. So, now let us look at what would you see in different layers of the solar atmosphere. Now, again as I mentioned that this modeling done is 1D modeling. It is considered that the solar atmosphere is plane parallel and is stratified, and therefore, you need to ask a question that how reasonable this assumption is. So, let us try to image different part of the sun and see if our assumption of one dimensional stratified atmosphere is valid. Right. So, what we saw here is an area taken imaged in the solar photosphere. So, what you see again is the granular pattern here. So, these are the granules, and then you have these two sunspots, right. There are dark features, there are various other features like umbra, penumbra, which I will mention later on. Now, let us go a little higher and try to image the same region in chromosphere, which is little higher or higher atmosphere than the photosphere, and that is the lower chromosphere. So, as you could see, the chromosphere was about 1000 kilometers. So, take the lower part and image the sun in that region. What you see is a completely different view of the sun. So, what you have, you still have the sunspots and your structures within that sunspot, for example, the what we call them light bridge, but in addition you see all these structures which is coming out of the sunspot region and fibrils and various dark and bright features, what was not present when you looked at it in the solar photosphere. Now, let us try to see again in the upper chromosphere, and what you see is a completely different view than what you saw in the lower chromosphere as well as in the photosphere. You retain the sunspots, but you have other brighter structures which are not present in either the photosphere or in the chromosphere. If you go even higher and try to image that in the corona, then you find a completely different structures, loop like things which are coming out of the sunspots. The sunspot region was here, and all those bright structure what you saw in the upper chromosphere, that all has disappeared. Now, since the sun's atmosphere is structured at very many different length scales and they are all evolving at different time scales, the consideration of the plane parallel atmosphere does not apply to any one particular region or one specific structure in the solar atmosphere. Rather, it gives an overall understanding of physical parameters like temperature and density, how it increases or how it decreases in the solar atmosphere with height, but does not apply for different specific structures, and therefore, one needs to essentially look into the details of these structures and their evolution separately. So, the large part of the solar spectrum is well reproduced in 1D models. Images taken at high spatial resolution demonstrate that the sun's atmosphere is highly complex and has structures at various length scales. Therefore, the 1D models, although they are good to obtain the average quantity relatively well, they are not applicable to any particular part of the sun's atmosphere. And what we understand today, that if we really want to put in all the structure you observe in different solar atmospheres, then there is a paper by Wedemeyer-Bohm where he has Wedemeyer-Bohm et al. Where they have attempted to put everything what they see in different layers of the atmosphere. So, you have these network regions, you have the granulars where you have the P mode and G mode you observe, the internetworks where the things are cooling and going down. You have the different kind of wave motions you observe. You have the spicules, which I'll show later. You have spicules of different types, and you have the transition region and all the way into the corona. So the atmosphere is essentially is a zoo where there are structures at all kind of length scales possible, and they are evolving at different time scales altogether. Now, let us look at each of these atmosphere in little more detail and see what structures do we see. So, let us take the photosphere, which is the lowest most, and it starts at the tau minimum. It starts at tau equals to 1 at lambda equals to 5,000 angstrom, goes till temperature minimum. What we see there, what we see particularly is the sunspot, faculae and granules, and this layer also shows the absorption lines. So, essentially the white light photons are coming, and you have the cooler gas in front. So, essentially it absorbs, the cooler gas absorbs different frequencies or different photons. It absorbs the photons at different frequencies, and it provides these set of dark lines which are called the Fraunhofer lines. The thickness of the photosphere is roughly about 400 to 600 kilometers. In white light, when you say, as I mentioned, that you have what you see is the sunspots, and then in the surrounding you have these dark regions which are uniformly going around the disk, and that what we call is limb darkening. On top of that, what you see is a number of sunspots depending on which day of the year you are looking at and which phase of the sun it is in, which I will talk about tomorrow. The number of sunspots can change. Also, what you see is these facular regions which are brighter than the dark limb region, so limb darkening. Now, why does the limb darkening happen? It should not happen, because if the sun is a uniform sphere, from any point you are looking at, it should appear the same. And it appears pretty uniform. That also has a reason. The reason is that when you are observing the sun, let us say you are an observer sitting here observing in this, that is a line of sight. So, when you are looking at the center of the sun or the disk, then this line of sight is penetrating only this thick gas, whereas when you are going to the towards the limb, then it has to penetrate through this large length scales, which is optically thick atmosphere. So, in this case here, for the same line of sight, you are penetrating deep inside the sun, whereas here you are not. So, you are adding up all the plasma, and that is why on the limb it looks darker and on the disk it looks brighter. This optical thickness is wavelength dependent, and we understand it pretty well, and that can be removed, and once that can be modeled and removed from the images you take, what you see the sun here is like a complete round ball and with a uniform brightness everywhere. Of course, you have the sunspots and other structures like faculae on the surface of the sun. What other things you see? You see convection again, the granulation, and we talked about it, the granulation bringing up the energy, and if you do the Doppler imaging, then you see that the plasma is, hot plasma is coming up and the cooler plasma is just going down as redshifted. The sunspots, if you take an image and observe the sunspots in its full glory, what you find that there is a dark umbra, and the sunspots could be as big as 10,000 kilometers. That means a factor of 1.8 larger or a factor of 2 larger than the diameter of the earth. What you see, there is a dark, which we call the umbra, and then you have the penumbra, which are the hair like structures which are coming out of the sunspot regions and going into the other part of the sun where you see the granulation. This is a sequence of images taken by Swedish solar telescope, which are showing all the way till you have the granules over here, but also you have at the same time observed umbra and penumbra of the sunspot. Now, why do sunspots look dark? Because I will mention tomorrow that these sunspot regions, they have a very strong magnetic field, and in the strong magnetic field region the convection is essentially quenched. Therefore, the plasma which is supposed to come through convection is not coming and is less bright, and also when you have, if you look at the formation of these sunspots, because the buoyancy, magnetic buoyancy to work, you need to have very strong magnetic field, and due to pressure equilibrium, then the density has to be, the temperature inside that tube has to be lower. So, if you, and that pops out, becomes a sunspot, and because the temperature is lower, you see the sunspots are dark. What you also see in these sunspots, apparently in these images, what you see that these filamentary structures seem to be going inside the sunspot, but that is a relative motion, because you see all these structures, the granules are coming up, and therefore, these structures are slower, and that is why they seem to be going down. But when you do the Doppler measurement, and that is what Evershed did, John Evershed from Kodaikanal Observatory in 1909, what he found that the radial flow of gas across the photospheric surface from inner border of the umbra towards the outer edge, and that is called the Evershed effect. There are some regions, some people claim that it is understood, but there is still a lot of work going on trying to understand that what produces such flows. In 2008, this discovery was celebrated by Indian Institute of Astrophysics, and a stamp was also given out from Government of India. Okay, let us look into the chromosphere. So, chromosphere is the region just above the photosphere, which is about 2000 or 1000 to 2000 thick. This region is highly inhomogeneous. The temperature in this region varies from about 10,000 to 50,000 degrees. The chromosphere strongly varies. It is very highly variable region on both spatially as well as temporally. And the structures you see, you retain the sunspots, but you also see plasmas, you see flares, you see fibrils, filaments, spicules, etc. and etc. In addition, you also see reverse granulation when you look into the calcium line, which observes the chromosphere. So, here for example, in the left you have an H alpha image, this one. What you see that these dark regions which are the sunspots, and then you have these strong bright regions which are plasmas, which you see them better when you observe them in calcium. So, you have the sunspots again, and you have these bright regions which are called the Plage regions in calcium K line. If you image the sun in H alpha and take a sequence of images, sometimes you do, if you are lucky of observing only a small region, sometimes you do see the strong brightening coming up, and this is a sequence of observations taken from Udaipur Solar Observatory, where you see all these dark regions which are the filaments, which we mentioned briefly yesterday and I will mention again today. But you also see that there are sudden brightenings taking place around this region, and then at the end you would see these loop like structures which are darker, they are forming, they are called the post flare loops. So, these brightenings are flares, and then you have the loops which are post flare loops. If you have a good resolution image, what you see that these are the filaments which are the dark plasma, dark structures, cooler plasma hanging into the atmosphere, and in the background you have this radiation. Now, imagine that this cooler plasma, which is about 20,000 degrees Kelvin, and if you go higher into the atmosphere, they are hanging in that atmosphere where the ambience is corona and it is 1,000,000 degree hot. What you also see that there are structures outside the limb which are brighter, they are called the prominences. Now, the difference between the prominences and filaments are nothing, but they are seen in absorption and emission. So, the prominences are seen in emission, the filaments are seen into absorption. So, if you wait for sun to rotate and this structure here goes to the limb, you will start seeing that appearing in emission. Now, if you take another sequence of image and you have to go to a space for high signal to noise ratio, what you see, so this is the solar limb again, these are sequence of images taken from Hinode solar optical telescope. What you see that there is a prominence here which is hanging into the atmosphere and showing all kind of motions, the wave motions, wave trains going from left to right. You also have structures where plasma is just going from one side up and then coming down from this side. In addition, you have these hair like structures which are always present there, they are evolving on the time scales of minutes, and of course, you see all these sunspot regions on the disk. which are appearing. So, these structures which are like hair like and always present, these are called the spicules, and the plasma which is just falling down, maybe because of thermal instability, they are called the coronal rains. So, it essentially seems like there is some rain of plasma occurring in the solar atmosphere from the corona. Now, if you go even higher resolution, so from Swedish solar telescope, what you see, there is supposed to be a sunspot here, and then you see all these structures which is coming out of the sunspot. There are various features which are becoming brighter and darker, that means they are essentially heating and cooling, and it is variable on length scales and on a time scale of minutes to hours. Now, if you go into ultraviolet and image on a very high resolution, so this is done from SUFI on board the Sunrise. On the left, you see this this is photosphere, and this is observing into chromosphere. What you see, there is a drastic difference between both these left and right images you see. So, these two can compare. So, this one is taken in the photosphere, this one is taken in the chromosphere. In the photosphere, you see this granulation, you have these bright blobs coming up and there is a dark lanes, whereas here in the chromosphere you have completely opposite. So, the blobs which are brighter in this, they are darker in the chromosphere, and the lanes which are darker in the photosphere, which are brighter in the chromosphere. So, that is what is called reverse granulation. So, completely opposite structure, and I will mention tomorrow that these are the regions where you have these lanes and these are bright regions. They are essentially having strongly magnetized, they are magnetized regions. So, if you take in between regions which are more sensitive to magnetic field, for example, so these are the bright regions. In the lanes, they are representative of magnetic field, and that makes it probably brighter. Now, let us go a bit higher and look at the transition region that essentially provides the interface between the chromosphere and in the corona. So, in the chromosphere you have a lot of radiation, and the energy is lost because of the radiation as well as the formation of various spectral lines. But in the corona you have mostly thermal conduction as a loss mechanism of heat. Now, transition region, how does it get heated? From about 20,000–30,000 to 1,000,000 degree, and there are various theories talking about it, but no concrete answer yet. Now, the transition region in physical terms, the way it is defined, that the location or the region where the thermal conduction from the corona, from being a cooling mechanism, it turns into a heating mechanism. So, thermal conduction from the corona can come down and heats the transition region. Now, transition region is fully ionized because the temperature goes all the way into to 1,000,000 degree, and then there are various emission line you start seeing because the density is low and is fully ionized. There are heavier elements, they get ionized and you start seeing emission lines. So, you have all the way from Lyman alpha going into neon 8, magnesium 10, and you go into the corona, you start seeing iron 9, 10, 11, 12. Till iron 17, iron 18, and so on and so forth. And depending on what line you are taking, you will see various different structures. So, the temperature in transition region changes from 50,000 to 1,000,000 degree. It is about 100 kilometer thick layer. If you image the transition region in the lower part of it, so if you take helium 1 or Lyman alpha or carbon 2, what you will see that the structures in that, they will look more like chromosphere because they are closer to the chromosphere in here. But when you go higher up and image the corona around this region in those lines, the transition region in those lines, they will appear more like what you would see in the solar corona. Heating is most likely due to heat conduction from corona and enthalpy flux from the corona. Now, the structures you see, they are mostly the foot points of the closed loops. You also see filaments, open loop, foot point of the open loops. In addition, you have lot of short low lying cool loops in the transition region. We call them cool loops because they are cooler than what the loops you would see up in the corona at around more than 1,000,000 degree. So, if you see, this is in the left here, that is an image taken in carbon 4. So, more like chromosphere. So, what you see all these network and inter-network regions. You also see here the plazas and the sunspot regions which are retained. So, these are lower transition region, they are appearing more like chromosphere. If you go higher up, now if you image the sun in these lines, what you also see now in complete opposite to what you saw in the when you image the photosphere, instead of seeing limb darkening, now you see limb brightening. So, you see a very nice ring around this, and that is essentially because now the plasma is fully ionized, less density. So, what you are seeing is optically thin plasma. So, when you are integrating along the line of sight, all the emission is being integrated and added up. So, here you have the line of sight is essentially increasing. So, you have more photons added, and that is why you see bright nice circular ring around the disk. Now, the transition region is very dynamic as well. Now, here is a very high resolution sequence of images put together taken by interface region imaging spectrometer, that is a NASA mission. And what you see that the transition region, there are structures which are everywhere and they are changing on a time scale of minutes and even longer. So, these structures, since this is lying in between the chromosphere and the corona, and as I argued earlier that the whole atmosphere is dynamically coupled, what these brightenings or these evolutions have to play a role in combining the chromosphere into the corona, and that is something which is being studied and not fully understood to date. Now, in transition region, in the upper transition region, you also see different kind of loop structures. So, that is somehow you can also call them in the corona. This is taken in iron 9, which is just below a million degree Kelvin, and what you see that these are the structures which are hundreds of megameters long, sitting on the surface of the sun, protruding into the solar atmosphere. Now, let us look into the corona, in the uppermost region of the atmosphere, where you see that the density has completely depleted. Now, it is 10 to the power 7, 10 to the power 8 per centimeter cube, where the temperature has gone to a million degree and more. So, above the transition region there exists corona, the temperature reaching up to about 2 million degrees. They are observed during solar eclipses. So, you saw them nice structures going around the occulted disk of the sun, and they are also seen in UV and X-ray. So, when you look at the solar corona during eclipses, what essentially you are seeing is like outside the plasma is around a million degree, the moon has blocked the disk, plasma is fully ionized, you have electrons and ions. Now, the photons from the background from the photosphere is coming and they are getting scattered. Now, more the scattering, more the electron density is. So, essentially the eclipse picture you take that demonstrate, or that is rather representation of the presence of electron density into the upper in the solar corona. Now, the moon comes once almost every year in front of the sun and between you to give you the total solar eclipse. So, if you want to observe the sun in its full glory, you need to create your own artificial eclipsing. And we know that why eclipses happen, because the angular diameter of the moon is essentially the same as the angular diameter of the sun on that particular day. You can create a disk which can mimic the moon, and that blocks the solar surface. It has been done from ground as well as from space. So, in this image here is taken from Mauna Loa Observatory in Hawaii, and this is done from in this one here is like blocking the sun's disk and about 1.05 or 1.05 or 1.1 solar radii, whereas here in this here is to look at even larger structures, you have to block the intensity is closer to the sun. So, that is the disk, and now you are blocking all the way till 2.5 solar radii, and you are observing from 2.5 to 6 solar radii, and you see all these structures protruding into the. So, the solar corona, the uppermost atmosphere, is visible to human eye only during eclipses or by means of artificial coronagraphs. Now, the solar corona can also be divided into various parts. Now, what is plotted in this here is the solar surface brightness, or the surface brightness. On x axis you have the distance from the sun center, the right y axis you have the electron density. It is just comparing different brightness. So, the electron density is just falling sharply, as you can see here in this curve. The surface brightness, this is the eclipse sky, this is the full moon, that is the day sky. So, in order to eclipse sky is less brighter than the full moon. So, you have to have a really clean environment to observe the total solar eclipses. Now, the corona can be divided into three parts. So, the K corona is essentially the inner portion of the sun's corona having a continuum spectrum caused by electron scattering. The F corona is the outer portion of the solar corona that consists of the sunlight which is scattered from the interplanetary dust between sun and earth, and the L corona is the emission line corona, and that can be observed in UV and X-rays. And if you do that, then you find images like that, and what you can then see that the corona itself has various structures on the disk. So, you have these really bright regions which are like closed loop like structures, and they are really bright, that we call them active region. And then you have the quiet part where is not much is seen, but only some bright dots here and there, that is called the quiet sun. And then you have really dark region which we call them as coronal hole. In addition, you have these bright dots appearing on the surface, and that we call them bright points. Now, each of these, the active regions, we find that they are very nicely correlated with the locations of the sunspots, what you find on the surface of the sun. Each of these, they evolve on various time scales. So, the active region can remain for like months, where the bright points, they have lifetime from few minutes to hours, and the coronal hole also can stay on the surface of the sun for about a rotation, which could be about a month. Now, if you take an X-ray image of the sun, put those image sequences together, you see that how dynamic the region which looked quite dark and nice and quiet, there is a lot of activity taking place in that as well. So, you have these bright points within that kind of structure in that kind of coronal hole, and you have all these plasma being ejected at time scales of minutes, which we call them solar jets. In addition to that, you also have very large flares. So, this is a Bastille Day flare which happened in 2002, taken by TRACE, and there are three different filters. So, the three different colors in this are representing three different filters, that essentially mean there are three different temperature of plasma, and you see only is a part of the disk very close to the disk center, and you see this sudden brightening appearing and formation of these loops, which you also see formation of those loops in the Udaipur Solar Observatory H-alpha observation flare. Now, the flares could be of different types depending on how energetic these flares are. The highest ones are called the X class flares, M class lower than that, C class, and B class is the lowest energy flare. Now, if you block the disk of the sun and you start observing even further out into the atmosphere in the corona. So, here is the disk of the sun, the white, and then you have the occulting disk, this is an artificial moon, much bigger than the moon. So, now we are observing from about 4 solar radii to 30 solar radii. You can see that the structures coming out of the sun, they are going all the way till 20-30 solar radius. This is one of the planets. That dark here is essentially the hand which is holding this instrument, and in addition to all these static structures which you see, there are various ejections which are coming out from the sun, and they are called the coronal mass ejections. So, if you look at again an image, a still image, so the disk and the occulting disk, and you have these structures which are coming out, they are going and moving into the interplanetary medium, and that is called coronal mass ejections. So, the average kinetic energy of such coronal mass ejections is about 10 to the power 29 ergs, and average speed they can travel to is like about 50 to 2,800 kilometers per second, and their frequency changes depending on the solar cycle, which I will talk to you tomorrow, but the solar cycle during the minimum when the sun is not that violent, you could see 1 coronal mass ejections in 1 day or 2 days, and about 6 to 10 coronal mass ejections every day when the sun is at maximum. Now, this is an example of a coronal mass ejection being seen in occulted image sequences. So, you see that there is ejection of plasma, and then you see all these kind of showered. So, energetic particles are showering at the detector. So, what is taken, these images are taken by the Solar and Heliospheric Observatory, which is at the L1 point. So, anything happening at the center of the disk. So, for example, there is a flare taking place here, very strong brightening that leads to ejection of this plasma. Plasma is being ejected. The whole thing is just coming and making your detector go blind, blind not in usual sense, but all these particles are being showered, and this is what you see detected by these energetic particles coming and hitting the detectors. And these could have very strong effect in space weather, such as power blackouts, satellite communication blockage, and so on and so forth. What other thing you see is essentially when you block the sun's disk, sometimes you see these comets are grazing into the field of view, grazing towards the sun. And what you see that there is this comet which is coming and grazing, going through. There were 2 tails, one is remaining vertical the way it is appearing, and the other fine tail which is always being radially outward from the sun. So, we know that there are 2 tails to a comet, one is the dust tail, the other is ionic tail, and it is the ionic tail which is pointing radially outside, as you can see in this grazing comet. And now we know that this is essentially because there is a constant flow of wind going out of the sun, this we call solar wind. And if you look at these measuring the speed, then what you find near the equator, they are done by Ulysses spacecraft. Near the equator you have the velocity distribution which is going at about 300-400 kilometers, whereas if you go towards the pole, then you have these strong wind which are going at around 800-700 kilometers per second. So, there are fast winds and there are slow winds. So, now we can put the whole thing in a perspective and see how we can see the solar interior as well as the atmosphere all together put on a scale. So, here you have again the interior, the radiative zone, the convective zone, and on the surface you see the chromosphere, transition region, the corona, and in the photosphere you see various structure. So, with that we finish with the solar surface and solar atmosphere and all these structures we see. In tomorrow's lecture we will talk about the sun's activity cycle, generation of magnetic field, and the role of magnetic field in explaining high temperatures observed into the upper layers of the atmosphere, as well as the region behind these ejections which are taking place, such as flares and coronal mass ejections into the upper layers of the atmosphere. So, in the next lecture we will be talking about the solar activity cycle, generation of magnetic field, and the role the magnetic field plays in explaining or in heating the upper layers of the atmosphere, which is much hotter than the lower layers of the atmosphere. In addition, we will also look into the roles magnetic field may play into the eruptions such as flares and coronal mass ejections taking place into the upper layers of the atmosphere.